Good afternoon, this is Schweitzer. We're going to do a little short introductory content video on bond energy. So what is bond energy? Well, in the end, really everything comes down to bonds and energy. So this can really be a situation where we can calculate everything based off just bonds. Now, in this case, there's a little bit of misconception with bonds, okay? And what happens when bonds are broken? What happens when bonds are formed? Well, so if I take and I have an atom and it has electrons around the outside, and I have another atom and it has electrons around the outside, and let's say they're bonded, okay? So what happens? Why are these two things bonded? Well, it turns out that this electrons are attracted to the other guy's nucleus, literally. And this guy is attracted to this guy's electrons right here, um, like that guy. So in this case, there is some repulsion here where the electrons don't like each other, but it would appear that the attractive forces, well, even though they're in balance um, with the repulsions, because it's like static, it's just in equilibrium or it's in stalemate. It's just sitting there. But um, in order to separate this atom from this atom, I'm going to have to break these attractions. I'm going to have to physically pull this one this way and pull this one this way. That's going to require energy. Okay? So, biggest thing people don't realize is that when bonds are broken, energy needs to be added. Added to the system. So, if you have a reaction that only breaks bonds, so we have energy, we have our system, and when you're adding energy to your system, you should realize that this is endothermic. So if you have a chemical reaction that only ever adds energy, only ever breaks bonds, then it's going to be endothermic. If you have a reaction that has to break more bonds than it forms, it's going to be endothermic. How would a reaction become endothermic? When you are breaking, you have to break more bonds um, than you form. Now, not every bond is equal. So some bonds are really energy intensive and some not so much. So you can't just go off quantity, but in general, you're using more energy to break bonds than you are getting energy back when you form bonds. So let's go here. What happens when bonds are formed? Okay, so now again you have a positive nucleus, you have a uh, positive nucleus, you got electrons, and you got electrons. And it turns out that when they're coming together and forming a bond, that again you have your attractive forces, and those attractive forces are bigger. The attractive forces is just as it's forming, the attractive forces are greater than the repulsive forces, which is the two negatives attracting, repelling, and also the two positives repel too. So any repulsive forces are smaller than the attractive forces. So really, when your attractive forces outweigh your repulsive forces, do you have to do anything? No, you just sit there and watch it happen, like two magnets just sticking together. So I don't have to do anything. I don't have to invest anything. All right, and in fact, when they attract, energy is released. In fact, the energy that's released is the same amount of energy that you would need to invest if you want to break it. So the amount of energy that is emitted from this thing as it's formed is called your bond dissociation energy. All right, so we call it bond energy. Another you might see as bond dissociation energy. Again, I just refer to it as bond, the energy associated with the bond energy. Bond association energy, dissociation. There's a lot of different names for it. Don't be confused by it. So how would a reaction become exothermic? Well, that means that, let's say, if you're just forming bonds, okay? If you're only forming bonds, okay? If you're only forming bonds, then you definitely would have energy leaving the system. And of course, you would have an exothermic reaction. So the question is there some sort of middle ground here between, bonds broken, bonds formed? Okay, so if you were to take, and have a reaction that breaks both bonds and formed bonds, okay, so reactions can both break and form bonds, right? So that means that we have energy that's both exiting and entering the system. Okay, so when you break bonds, all right, so when you break bonds, we're going to have energy entering the system. When you form bonds, we're going to have energy exiting the system. And really, we just need to add that energy up. Who won? Which one was more? Here's the formula for that. We call it, it's just going to be delta H once again. Okay, and this is going to be in energy per mole, typically kilojoules per mole. The sum of all the bonds broken bonds broken this is in the reactants, okay, minus the sum of the bonds formed. Now this is a little bit, it's reactants minus products, and a lot of other calculations are backwards. So this is something that be aware of, is reactants minus products. Okay, so let's just try an example. And this is the example I'm going to do right here. I'm going to flip to a different page here, and I'll do this example. Methane burning. We know this is an exothermic reaction. So let's just do that one here. I got CH4. Now, it burns an oxygen, so we obviously have bonds that are being broken and bonds that are being formed. And we're going to form CO2 and H2O. This is a great problem because it involves also everything from bonding to atoms to energy to stoichiometry. So it's got a lot of stuff and therefore it's utilized a lot. First thing we do is we balance it. Okay, so one carbon, four hydrogens, two oxygens, 2 and 2 is 4, so I need a 2 here. Okay. Now, what bonds are being broken? So you gotta sketch out a Lewis structure. I'm gonna go through a little process reminder how we do this. First we do is we add up the valence electrons. So carbon's gonna give me 4, Hydrogen's going to give me 1, and but there's 4 of them. So I get 8 valence electrons. So carbon, single bond hydrogen, single bond hydrogen, single bond hydrogen. That's my minimum bond. So 2, 4, 6, 8. I've used all my electrons up, and everything is satisfied. Remember, hydrogens can only bond 1 time, and the carbon has 8 electrons now. Carbon bonds 4 times. Oxygen. Okay, there's 6 valence electrons. There's 2 of them for 12. All right, oxygen, single bond oxygen, 2, 4, 6, 8, and 2, 4, 6, 8, 10, 12. Notice I'm short a pair. I'll take off a neighbor and share between. Now, I have a double bond here. Now there's 2 of them though. So I'm going to draw another one. All right, CO2. I got 4 valence electrons. I have 6, and there's 2 of them. So we got 12 plus 4 more, 16 electrons. Okay. Carbon, single bond oxygen, 2, 4, 6, 8, 10, 12, 14. So you can do either way. Put here 16. This guy's short 2 pairs. So take a pair off this guy and share it there. Take a pair off this guy, share it here. Okay. This is the most standard way in which we show carbon dioxide. You can, however, do it this way. There's more. When you get into it, you'll get a little bit more involved. You can get something looking like this. Okay. You'd have a resonance structure going back and forth and like that. So, I mean, there are some differences, ways that we can draw things on paper, but it turns out in nature, this is what it looks like. Okay, water molecule. There's only one of those. Water molecules, of course, are just H2O. And I have 2 of those. So you can see it's got a lot of stuff here that we have typically hadn't done for a while. I'm breaking these bonds, and I'm forming these bonds. So typically we'll have a point associated with just with assigning what's being broken, what's being formed. I'm going to break 4 of my CH bonds, and I'm going to break 2 of my O double bonds, and then I'm going to form my 2 of those guys. I got 1 here and 1 here, so 2 O double bond carbon, and I'm going to form 4, 1, 2, 3, 4 of my OH bonds in my water. The rest of this is really, this is just a procedure, and drawing these structures out might be the hardest part if it's been a while. The next thing we do is we go in our workbook. You'll find this particular chart. It looks like this, and you literally just grab a value off here. You find it. So our first one was the carbon-hydrogen bond. Okay, so we have this carbon-hydrogen bond, and it's going to be located right here. 99. Let's go over here. So 4 times 99. Okay. 2 of these guys, the oxygen bond in O2. Let's find it. Okay. And I think it's over here. There it is. 119. Okay. 119. Now the formula does say that we sum or add up all the broken stuff here. So we're gonna multiply these and add them all up into one lump energy for breaking. Well, let's grab these 2 numbers first. O2 for the carbon dioxide, I got 2 of those guys. All right, and you'll find that they have one here, and it actually says O2 on it. Where is it? Oh, right there. So this is a carbon double bond oxygen 4CO2, 192. So 2 times 192. And then this one is an OH bond, Let's go find that guy for the water molecule. And here we go, 111. Okay. 4 times 111. Add up all of these guys. This is a sum of all my broken minus the sum of all my formed. Let's grab a calculator. All right. 4 times 99 is 396 plus 2 times 119, 634. So this whole thing I got was 634 minus, let's do all of our products, all the stuff for breaking. 2 times 192 is 384 plus 444, 828. Now, of course, we know this reaction is exothermic, 828. All right, and in the end here, what do we get for our final subtraction? 634 minus 828. 634 minus 828 equals 100, negative 194. And this is going to be in kilojoules per reaction cycle. We did it for just the one reaction cycle. We added up all the individual moles for each one of these guys, 2 of these and 2 of those, just 4. Anyway, so this is my delta H. And that's the only example we're going to show here. You'll have to just try a couple on your own. Now, is this example perfect? You know, are there any issues with this calculation? And the answer is yes, this is not maybe the best calculation we'll get. These bond energies do vary. Notice they have a specific bond energy for CO2. So this is only counting covalent bonds. And this can sometimes vary, like between bonds. It's not counting any intermolecular forces. So it's not really counting whether the water is a solid, a liquid, or a gas. Okay? Solid, liquid, or gas. So there's issues there. So our numbers versus other ways that we can calculate out bond energy, this might be more of an approximation than the other ones. Either way, because it contains so much other stuff that general people in chemistry like, this is a pretty common calculation. Thank you.